When dealing with motion, problems can be solved by kinematics, describes in terms of velocity and acceleration. But how object moves as it does? What makes an object at rest begin to move? Force is needed for the object to move. And this concept is under dynamics in physics. Force is any kind of push or a pull of an object and causes it to move. A certain object from zero velocity, when force is exerted, moves to a non-zero velocity. Force is exerted when you push a grocery cart, an elevator lit by a motor, a hammer hits a nail, or when an object falls because of the force of gravity. Spring scale is used to measure the magnitude of a force. Commonly, it is used to find the weight of an object, that is, the force of gravity acting on an object. Spring scale is also used for measuring other kinds of force, such as pulling forces. Force has magnitude, as well as direction. Therefore, it is a vector quantity. Force can be represented by arrows in a diagram so that it will be easier to solve such problems in physics. Force is needed in order for an object to move in a horizontal plane. An object is naturally at rest. When force is applied, the object will move. The greater the force is exerted, the faster the object moves. I disagree. It's just natural for an object to be in motion. If no force is applied to a moving object, it will continue to move with constant speed in a straight line. Thus, an object slows down only when force is exerted on it. There is actually friction acting on an object, that's why force is needed to push or pull an object. While pushing a grocery cart, force from your hand balances the friction in the floor. Brilliant idea. All credits to Galileo for such wonderful idealization. There are 3 Newton's laws of motion, from which the first law was derived from Galileo's idea. The first law states that every object continues to stay at rest, or in motion along a straight line, as long as no net force acts on it. The tendency of an object to maintain at rest, or in motion in a straight line is called inertia. That's why Newton's first law is called law of inertia. From Newton's understanding, mass is a synonym for quantity of matter. But in a more precise way, mass is a measure of inertia of an object. Remember that inertia is the reason why an object stays at rest, or keeps moving. More mass means more inertia. The mass of an object, the greater its tendency to resist change. Example, a huge building is so massive that a person cannot move it. It has more mass compared to a person, thus, it has more inertia. Unless much greater force exerted, then it will move, or even destroyed. Mass standard unit is kilograms. Now, what distinguishes mass from weight? Weight, on the other hand, is a force, that is, the pull of gravity acting on an object. To understand, suppose Neil Armstrong, with his heavy spacesuit and backpack, weighed 1600 newtons here on Earth. As he landed to the moon, he found out that he weighed 270 newtons. Since the force of gravity in the moon is weaker, Neil Armstrong weighed lesser. But his mass remains the same in both locations, as well as the amount of matter and inertia. Solving problems regarding forces needs understanding of Newton's second law of motion. And that's what we're going to talk about. If force is exerted to an object, then it will change its velocity. For an object at rest, the velocity will increase. For an object already in motion, if there is force acted on it in the same direction, velocity will increase. But if force is applied in opposite direction, the object will slow down. From kinematics, we can recall that the change in velocity is acceleration. Therefore, we can say that the net force causes acceleration. Take note that acceleration depends on the mass of an object. The greater the mass, the less the acceleration for a certain net force. This relationship is stated in Newton's second law of motion. The acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. Since force is a vector quantity, as well as acceleration, both has the same direction. The second law of motion is represented by this equation. The standard unit of force is in Newton. To every action, there is an equal and opposite reaction. This simple statement is the principle of Newton's third law of motion. As an evidence, if your hand pushes a table, you are exerting force on the table. At the same time, the table is also exerting force on your hand. You can feel it because it hurts. Newton wants to express that exerting force is not one-sided. In physics terms, whenever an object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first object. The propulsion of rocket is explained by Newton's third law. Most people think that rockets accelerates because of the gases coming out at the back of the engine push against the ground. That is completely incorrect. What actually happens is that the rocket exerts strong force on the gases, and the gases exert an equal and opposite force on the rocket, which makes the rocket propel forward. Gravitational force acts vertically downward to the center of the Earth. Relating it to Newton's second law of motion, the gravitational force is equal to mass times acceleration due to gravity, 9.8 meters per second squared. Suppose that Ted is standing in an elevator. He is 50 kilograms. The elevator begins to accelerate upward at 2 meters per second squared. What is the support force needed for the elevator to accelerate upward with Ted? To calculate, the equation of the support force is the sum of the net force by the elevator's acceleration and Ted's weight. The net force is 50 kilograms times 2 meters per second squared. Weight is equal to 50 kilograms times 9.8 meters per second square. Therefore, the support force is equal to 590 newtons. The support force is greater than the weight. That's why we feel heavier when the elevator accelerated upward. The downward force or the gravitational force needs to balance with the upward forces or the elevator's acceleration. Sheldon was on his way home when his car got stuck in the mud. He ties a strong rope to the back bumper of the car and the other end to a boulder. He pushes the middle of the rope with his maximum effort. He estimates the force to be 300 newtons. The car began to budge with the rope at an angle he estimates 5 degrees. With what force is the rope pulling on the car? Assuming that the mass of the rope is negligible. To solve this, it is important to draw a free body diagram that represents the given and the unknown. 300 newtons is along the y-axis, denoted as Fs, or Sheldon's force. Must also label other forces involved. The unknown is tension that is present in the rope to move the car. With simple knowledge in trigonometry, we can manipulate this equation to come up with something useful to solve the problem. Take note the acceleration in the x and y axis is equal to 0. Therefore, both force vector components in the x and y axis are equate to 0. The force produced on the car is equal to 1700 newtons. Some of physics problems are not taking account on friction, which exists between two solid surfaces. This must be considered because even the smoothest looking surface is rough in microscopic scale. There are two types of friction: the static friction and kinetic friction. Static friction refers to a parallel force to surfaces that can exist even when they are not sliding. Suppose a box is resting on a horizontal floor. If you try to push the box, you are exerting a horizontal force. But if it doesn't move, it means that there is another force on the box keeping it from moving. This force is the static friction exerted by the floor on the box. If you exert greater force without moving the box, the static force increases. But if you push hard enough to move the box, then kinetic friction takes over. When the box moves because of the greater force you exerted, the maximum force of static friction was exceeded. These are the equations defining friction, which are experimental relation between the friction force and the normal force.